Hello, this is Professor Keen. Today I want to talk about the analysis of the relativity lab. You'll remember in the relativity lab, what we did is we first suspended a 500-gram weight from a force sensor in the laboratory. And then what we did was we suspended the same weight from the same force sensor and placed it into an elevator and ascended and then descended and measured the weight of the object in those situations. So in order to understand the effect of acceleration upward and downward, let's take a look at a free body diagram. This will help us to understand what's going on. So let's imagine, let me go to this toolbar. If we have an elevator, I'll draw a box here. This is supposed to represent our elevator. And instead of drawing it suspended from a force sensor, let's just imagine the object is suspended from the ceiling and we're measuring the weight of the object. Okay, so here's our suspended object in this elevator. Now let's draw a free body diagram. So the free body diagram consists of, here's our mass, that's our 500-gram mass. There are two forces that are acting on this mass. The first force, of course, is its own weight, which is just mg, right? The second force is the tension in the string. Now remember, what you're basically doing when you weigh an object, you're not directly measuring its weight. Technically speaking, you're measuring the tension in the string. You might think about, like, this is similar to when you're standing on a spring scale in your bathroom. What the spring scale does is it doesn't directly measure your weight. It measures how much the spring scale is compressed, and it has that calibrated, so by the compression it's inferring how much you weigh. Similarly, when you suspend something, the force sensor is measuring the tension in the string, and from that tension it's deducing what your weight must be. Okay, so let's write down, we've just written this free body diagram. Here's the mass, there's the two forces acting on it. Let's now write down Newton's second law. So the upward force, let's call the positive direction. The positive direction is upward, the negative direction is downward. So we'll have tension minus weight equals mass times acceleration. So this is the sum of the two forces. Here is mass times acceleration. Okay, now I want you to consider, well, let's go ahead and plug in mg for the weight. Tension minus mg equals ma. Now I want you to consider two cases. The first case is where acceleration is equal to 0. That is when the elevator is not accelerating. And then I want you to consider the case where acceleration is not equal to 0. That is, the elevator is accelerating. Okay, so what happens when acceleration equals 0? Well, Newton's second law, if acceleration is 0, we just get T minus mg equals 0, or tension equals mg. In other words, the tension that is in the string, the tension force, is just equal to mg, or the weight of the object. So the tension equals the weight of the object. That's analogous to the case where we're in the laboratory, we were measuring the tension or the amount of stretching of the spring scale or the dual range force sensor and inferring the weight of the object. Now what happens when the acceleration is not equal to 0? Then we have tension minus mg equals ma. Acceleration is not 0. And remember, we're still just measuring the tension in the string while we're in the elevator. So tension equals mg plus ma, or if we factor out the common factor m, we have g plus a. Notice that when we measure the tension in the string, or the amount of force that the force sensor detects, we're not just measuring the weight of the object, we're also measuring ma, right? It's almost as if g, which normally is 9.8, is supplemented by whatever the acceleration of the elevator is upward. So if the elevator is accelerating upward so that a is positive, we're detecting a tension as if g was 9.8 plus the acceleration of the elevator. In other words, the tension exceeds the ordinary tension when the acceleration is not equal to 0, and specifically when A is positive. And also notice that the tension is less than the ordinary tension when the acceleration is negative. So when you're accelerating downward or when the elevator is decelerating. This corresponds to your common sense that when you're standing in an elevator, you feel your normal weight, for example, but the moment the elevator begins accelerating upwards, suddenly your body feels a bit heavier. It's almost as if the gravitational acceleration is momentarily increased. That is the sensation you have because you are in an accelerating reference frame. Then, when the elevator stops accelerating, when it's going at a constant velocity straight upward, the acceleration is 0, and again, you feel your normal weight, and the tension in the string is the normal tension that would be experienced by a stationary object. And then, when you get to the top of the elevator ride, what happens is the elevator decelerates, the acceleration becomes negative, and suddenly, you feel a bit lighter for the moment, or the tension in the string is suddenly reduced by a bit. So this is precisely what we expect to see when we're measuring using the force sensor, the weight of an object riding up and down in an elevator. So let's go ahead and open up our lab experiment and analyze our data. Okay, so here are our two data sets. The red one corresponds to when the elevator is ascending. So here in this section, the initial section, the force we're measuring, this is force as a function of time, the force we're measuring is the tension in the string before the elevator starts moving. And it's about 4.9 or so. I can do some analysis here. If I select this section right here, do statistics on it, going up force, okay. The force, the mean value is 4.905 in that section. So that's the number of newtons of tension in the string, and that is equal to the weight of the object. Now in this section between, let me look here, between this time right here, that's about 3.7 seconds and about 6.4 seconds, that interval right there, the elevator is accelerating upwards, so the tension in the string suddenly increases during that time interval. Then the elevator has stopped accelerating, and here it's going at a constant velocity upward. And during that time period, the weight of the object, well, the tension in the string, again, represents the weight of the object. So here, this region, the mean value should be the same. Yes, it jumps around a little bit, but that's probably because the elevator is bouncing a bit. Then when you get to this point right here, the elevator decelerates, and so the tension in the string drops momentarily. And then right here, the elevator's kind of bouncing up and down a little bit, but it comes to a rest, and there you're sitting at the top level of the building. Okay? So then the blue trace, on the other hand, represents the going down trip. Now notice that it's shifted downward a little bit. I actually don't know why that is. I suspect that we messed up our calibration. We had to shut things down and start them back up before we went down, so we didn't keep our calibration. So the force is reading a bit differently here. That's probably okay because we're going to subtract off, we're going to normalize this anyway. But I just wanted to point that out at first. So here, the tension in the string is constant. Here, suddenly the elevator begins going downward. It accelerates downward or decelerates, and the tension in the string drops for a short period of time. Here, we're going downward at constant speed, and here the elevator hits the bottom, and it accelerates upward, and so suddenly the tension, it gets heavier for a moment, and here's where we're at the bottom of the elevator shaft. Okay, so what I'm going to do is I'm going to take both data traces, and I'm just going to subtract off the weight of the object or the tension in the string that corresponds to the weight of the object. So if we look at this right here, once again, I'm going to do a statistical analysis. This was the going up force was mean value for, let me do that again. Let me select all this data set right here. So right there, do statistics. We're going up. 4.904. So I'm going to create a new data column, data, new calculated column. And I'm going to say this is going to be the tension minus mg. T minus mg. And the units are newtons. And to calculate this, I'm going to do two specific column, the going up force, and subtract off 4.904. That was the mean value. So done. Okay, so now I have a new column right here, and I'll plot this in a moment. And yeah, I'll go ahead and plot this now. So instead of force here, I'm going to plot T minus mg as a function of time, and I'll auto scale it. So now notice what I've done is this is a plot of the tension minus mg, and I've subtracted off the constant part, so it's 0. And so this right here, if we go back to our spreadsheet, what I've done is I've plotted on the vertical axis T minus mg, the tension in the string minus mg. So what I'm plotting now is the product mass times acceleration. So this is a plot of really the mass times acceleration versus time. Now what I'm going to do is I'm going to create a new column because I want to plot the acceleration as a function of time. So data, new manual column. I'm going to call this acceleration, and yeah, acceleration, and cancel. Data, new calculated column, sorry. This will be in meters per second squared, and I'm going to plot T minus mg, and I'm going to divide this by the mass of the object, which was 500 grams. Done. Okay, so here, right there, now I'm going to adjust this. Now instead I'm going to plot acceleration and auto scale it. Okay, so now what I'm plotting is the acceleration of the elevator as a function of time. And you'll see here on the way up, the acceleration starts out at 0, then it accelerates, then the acceleration goes away, and I'm going at a constant velocity, then it decelerates, and then it goes at a constant velocity. All right? And now finally, remember, so I'm now plotting the acceleration as a function of time, right? Now remember that if we want to find the velocity that an object is moving at, you need to integrate the acceleration over time between time 1 and time 2. The integral of that is going to give you the speed of the object, or rather the change in speed. Okay, so how can we do that using Logger Pro? So if we select this data set between here and here, and we carry out the integral, the going up, okay, so the integral is 0.000715 meters per second squared times seconds. So 0.000715. Oh, I did something wrong. What I did is I divided by 500. I should probably have divided by 0.5. So let me do this again. Instead of dividing by 500, it was 0.5. Okay. Done. Okay. Rescale this. Okay, now I got the acceleration correctly. So now I'm going to integrate this by going up data. And so the integral is 0.7227 meters per second squared times second, or 0.72 meters per second. So I just found that the integral of this, the area under that curve, was 0.72 meters per second. So that is the difference in velocity from the initial time to the final time. So the elevator went from a speed of 0 initially. So the speed initial, when it was sitting at the bottom, was 0. The speed final after it accelerated was 0.72 meters per second. That is the speed that the elevator has on the way up. And then presumably, if I go back here and I do the integral of this curve right here, hopefully I'll get the same answer. So I'll integrate right there. 0.661. Well, it didn't turn out quite so well. So that is the speed. This is the speed. The integral here is the speed gained going from 0 speed up to the final speed of the elevator. And then when it goes from here, from the speed going up, it has to come to rest right here. It should lose all 0.72 meters per second. It lost 0.66 meters per second. Oh well, so this is the speed on the way up. On the way up. And it should have lost 0.72 when it got to the top by decelerating, but we didn't quite get that. It lost 0.66. We know it did come to a rest, but our calculations didn't quite work out as well as we'd hoped. Okay, let's analyze the other data, the data while going down. So, data going down. Did I calculate this right here? Well, tell you what, I think you get the idea for how to do this analysis. And let's plot this data right here. It looks like I can plot two of them at a time. Going up, it's plotting it. Going down while it's plotting it. Oh, that one I have to do correctly. 0.5. Okay. And let's auto scale this. Okay, I just made a correction here. So here I've showed the acceleration as a function of time for going up. And then what I can do is I can click over here. I made the same corrections that I did before. And let's look at the going down data. Look at acceleration. And here is the going down data. It starts out when I'm at the top. There's 0 acceleration of the elevator. And then it decelerates. That means it accelerates downward and goes at constant speed, and then when it gets to the bottom, it's an upward acceleration and then stationary. So you can figure out the speed of the elevator while it's going down by taking the integral of this region right here. I'll integrate it. So it looks like on the way down, it goes from a speed of 0 to a speed of 0.42 meters per second on the way down. And then when it gets to the bottom, it should, of course, lose that speed. We'll see if we get lucky and this works out the same way. There we get a 0.38. Maybe the limits of integration should be a little bit different. It's probably pretty sensitive to the limits of integration. There we go, 0.405. That's not so bad. Okay, so here it starts with 0 speed. It accelerates downward. Now it has a speed of 0.42 meters per second. When it gets to the bottom, it accelerates upward, loses 0.41 meters per second, and then it's stationary here. Again, these integrals should work out exactly equal, but I think it's really sensitive to how I pick my limits of integration. So I've just shown you how you're able to find the velocity or the speed of that elevator. By the way, if you want to know how high the elevator went, you can, of course, take this velocity right here, the speed that it's going, multiply by the amount of time that you're traveling. So for example, we know on the way down, it's going at a speed of 0.42 meters per second downward. And then if I take this time interval right here, which has, that's 17 seconds about, I take that speed times that time to figure out the distance that it traveled while it's moving at constant speed. And that will give you an estimate of how high the elevator shaft is. Okay, I'm going to stop there and let you work on the analysis.